So far, in traditional object storage systems, we only talk about put and get, but we do support some additional things. So if put and get are not enough for your application, we do support a few atomic operations. We support test and set, append, increment. And these are pretty trivial to implement in CRAQ. And the reason for this is that the head of the chain alone can evaluate the query. So the head can figure out what the latest version is, do a test and set, and then propagate it down the chain. You could also imagine multiple object transactions. So for example, if you wanted to test one object and set another, if multiple objects are on the same chain, then this is also easy for us to do because the head, again, is the only replica that has to be involved in this transaction. And it can just propagate it down the chain. So the tricky case comes when we have objects across multiple chains. If you have a test and set for an object on one chain and set on another, then you could use an agreement protocol between the heads of the chains. What's nice here is that only the heads have to participate in the agreement protocol, but it would degrade performance because the heads would have to do some locking. So this would have to be used carefully by applications. So that's it. So to summarize, CRAQ's contributions challenge the trade-off of consistency and throughput. And we do this by providing the strong consistency guarantees of chain replication, but allowing throughput to scale linearly for read-mostly workloads. We can support wide area deployment of chains naturally, and we have some atomic operations and transactions. And that's it. I want to thank you for listening, and I'll take questions.
Hello. Hi. So this is pretty cool stuff. So I got a question about the results that you showed for the read operations that complete when you have a failure in the replica chain.
Yep.
And so what you showed is that the replica comes out, and then you see the number of read operations that successfully complete go down for a bit, and they come back up again.
Yep.
So I'm wondering, how is it that they come back to the same level if presumably you have one less replica on the chain? I mean, are you bringing something back up and then copying all the state over from the failed replica? And if so, how long does that take?
Yeah, so we are actually bringing a new replica into the chain. So it makes the throughput go back up. And so you can see in the graph there is a small, let me bring it up. There is actually a small period when the throughput goes back up, and this is when it has to transfer the object to the new replica. So but these are all in memory, and we're only talking about one object here. So it takes a short amount of time to transfer that state. Now, alternatively, if we, you'd imagine in a real application, you'd have lots of objects and lots of state. So when a new replica joins, it would have to catch up before actually joining the chain.
Okay, makes sense.
So more of a comment than a question. The implementation of appends in the Hadoop distributed file system essentially needs exactly something like this. So please consider contributing this to that work.
Okay, thanks.
So in the case of a data center getting partitioned, how would you make sure that writes only occur in one of the data centers? You mentioned the master data center concept. So does that have to be statically defined for each piece of data, which one the master data center is going to be?
So writes only occurring in one data center is really just an optimization. So it could be that you could still have writes from other places. It's just that if the data center, if a write from data center 2 can't reach data center 1, then it wouldn't be able to write to the chain. So I'm not sure I understand your question fully, but.
So let's say you have data center DC1 and DC2, and you have replicas of the same data both in DC1 and DC2. And DC1 and DC2 are partitioned. And you have a write which originates in DC1, and you have a separate write which originates in DC2. How would you handle that case?
So in the case when there is no master data center?
Yes, or if there is a master data center, does that have to be statically defined? And if so, there are obvious implications for that static definition.
Yeah, so it does have to be statically defined. So we don't support, if there are partitions and there's multiple, so we use majority. So if there's only 2 data centers, neither data center would have the majority if there is no master data center. If there is a master data center, then the one that's the master can commit writes, while the one that's not the master would become read-only or turn off.
Okay, thank you.
So I have a question also, which is, so I would say that it feels to me like one of the contributions of this work is to show that this single substrate of chain replication can also have multiple properties simultaneously. It can not only have high write throughput, it can also have high read throughput. And looking at some of the things that were done in, say, the scheme that you compared against initially, where a single primary multicast out all the write operations, that seemed to make a different trade-off of having lower latency but lower write throughput. So I was wondering what your thoughts are on whether it's possible to have a single substrate that scales across that wider range, where it not only can have the, well, as the original chain replication did, the high write throughput, as your work does, the high read throughput, but in the original scheme that you contrasted with, that lower latency on writes.
So that's definitely a problem in our system with write latency. And so the multicast does help a little bit, but we still have to wait for it to propagate across multiple data centers, which could take a long time. I don't have a good answer for you. We're still working on how to reduce latency.
I have another question,
Okay.
which is a lot of storage systems have things that aren't in memory. How do you feel your system would change when many of the operations didn't occur only in memory?
So I think our implementation would become more complex, but I think the protocol itself would pretty much stay the same. I think it becomes trickier when we add new replicas to the system. When we do failure recovery, you have to deal with a slow disk and with a large amount of data. So our current implementation is just in memory, and we haven't done that yet, but we plan to do that soon.
If there are no other questions, let's thank the speaker again.